Representing text is the character set idea from the last lesson, applied. Every character you type is looked up in the character set, which gives a code. That code is stored in binary, and to display it again, the process runs backwards. The binary is read, the number is looked up, and the matching shape is drawn on screen. The important consequence is that the text does not exist in the machine in any form you would recognize. What exists is a sequence of numbers and a character set that says what those numbers mean. Change the character set and the same bits become different letters, which is exactly what happens when a file opens as Mojibeki, all question marks and strange symbols. The bytes were fine. The agreement about what they meant was lost. Some vocabulary the exam uses precisely. A bit is a single binary digit, a 0 or a 1. A byte is 8 bits. A character is one letter, digit, symbol, or space. And note that a space is a character, which is a detail worth remembering when counting. A character set is the agreed mapping between characters and codes, and a character code is the specific number assigned to one character. Where students lose marks is confusing bits with bytes. The formula gives you bits, and questions frequently want bytes, so the division by 8 is a step you have to remember to do. So let us calculate 1. The formula is file size equals the number of characters multiplied by the bits per character. Take a sentence, the cat sat, 11 characters, and count the spaces, because they are characters too. THE is 3, space is 4, CAT takes us to 7, space is 8, SAT is 11. Stored in 8-bit ASCII. 11 times 8 is 88 bits. Now convert to bytes. 88 divided by 8 is 11 bytes. And notice that the number of bytes equals the number of characters, which is always true for 8-bit ASCII and is a useful sanity check. Now store the same sentence in 16-bit Unicode. 11 characters times 16 bits is 176 bits, which is 22 bytes. Exactly double, because each character now needs twice as many bits. That is the storage cost of Unicode made concrete, and it is the calculation a question is really asking for when it says compare the file sizes. 3 factors affect how much space text takes, and a question may ask you to name them. The number of characters, obviously, more text, more storage, and the relationship is directly proportional. The character set used since ASCII at 8 bits and Unicode at 16 or 32 give very different totals for identical text. And whether the file is compressed, which we cover in 1.3, text compresses extremely well because natural language repeats itself enormously. What does not affect it, and this catches people out, is the content of the text. The word cat and the word dog take exactly the same space. So do a page of meaningful prose and a page of random letters. The computer stores a code per character, regardless of what those characters spell. One consequence of characters being numbers that questions do test. When text is sorted or compared, the computer compares character codes. That has 2 visible effects. First, in ASCII, every capital letter has a lower code than every lowercase letter. A is 65, A is 97. So a naive sort puts all capitalized words before all lowercase ones regardless of alphabet. Sorting apple, banana, and cherry gives banana first. Second, digits have codes too, from 48 for 0, which is why numbers stored as text sort in a strange order. As text, 10 comes before 9 because the comparison looks at the first character and 1 is less than 9. That is a real bug in real systems, and it is the reason a value you will sort numerically should be stored as a number rather than a string. The point made in topic 8 about choosing a data type. Exam questions often ask for an estimate on something larger than a sentence, so let us scale it up. A typical page of prose is around 500 words, and an average English word is about 5 letters plus a space, so roughly 6 characters per word. 500 words times 6 is 3,000 characters. In 8-bit ASCII, that is 3,000 bytes, since one character is 1 byte, which is about 3 kilobytes. Now compare that with an image, which is the next lesson. A single photograph from a phone is commonly 3 or 4 megabytes. so one photograph is worth roughly 1,000 pages of text. That comparison is worth carrying because it explains something you have experienced. Why a document full of pictures is enormous while the writing in it costs almost nothing, and why text was the first thing computers handled well. It is by far the cheapest media type to store, and by a very wide margin. 4 things to take into the exam. First, know the formula. File size equals number of characters multiplied by bits per character. Second, watch the units. That formula gives bits, so divide by 8 if the question asks for bytes, and say which unit your answer is in. Third, count every character including spaces and punctuation. Omitting spaces is the commonest arithmetic slip here. And fourth, when comparing character sets, do the calculation both ways and state the ratio. 16-bit Unicode is exactly twice 8-bit ASCII for the same text. Showing the working matters because these questions award marks for the method as well as the answer.